So now what we're going to do is to calculate the remaining useful life of our engines. If you look into our data, what you can see is we have the engines here, engine 1, and the time in cycle keep increasing. As it keep increasing, it will get to the point that it cannot increase because the engine failed. So the maximum number, for example, of this, for example, engine 100, the maximum value we have is the 200, which is the maximum cycle this engine has. So what we need to do, we need to 200, we first detect when the engine will fail, the maximum cycle every engine have, and then what we need to create another column that have the remaining useful life for every line, that is the max minus how many cycle this engine is running, like the current cycle. So what we will do is we will first find the maximum number of every engine, like life. So the maximum, so every engine going to run until it reaches a maximum number. We need to find this maximum number automatically for all the engines. So this is our first step. Next step, we will explain it as we go. So the first thing is we df train RUL. This is, we create another data frame that we built based on our previous data frame. Of course, this is going to be as we did in place. We actually we use it with this data frame, that is, we consider the one without the with the dropped values. So you can see here that it's 18 columns that got dropped from, I think, 26. So from 26, the last one. So we don't have to, of course, create a data frame, a new data frame. We'll just group by with using the latest one. And we do here, we just write the engine. So we group by the engine, and then we aggregate these values based on only this the cycle the time in cycle has to be max. Yep. We look at it now. Our group. So we see the DF now. So these are the engines, and these are the maximum possible cycles for every engine. Now what we will need to do, now here in times in cycles, here the engine, what we need is, now we need to merge the df train RU with our main data, which is df train. However, we have to understand one thing, that is the df, we cannot use time in cycles. So what we need to do is to rename this to something else, for example, life or engine life. So df train RU dot rename and column equal, we from this one, time in cycle become life. and of course we say in place. This equals true, and we run it. Now we can see how it looks. So now we have engine and then live. So now what we need to do is to merge df train will equal df train dot merge df train rul on the common thing they have, and merger is basically we have now two data sets. One has engine and live, and one has many engines and other data. So what we need to do, we need to add these live into every engine they have into the original data set. So we run it like this, and then we just write df train and see how things look. Df now we should see it live. Yeah, the live is here. Now we don't need to keep it, but yeah, it's because it's kind of tells how much life. So if you're in having the specific cycle and you want to create a test data and you have already know when it will fail, you cannot really use it. Like it's not logical. So what we will do is we write one more column, that is the df train. We need to subtract df train. We will create a new remaining useful life. This is going to be our when we train, we have x train, like the data's input data, and the data we need, or the value we need to predict, which is remaining useful life. So this is the remaining useful life, and here it has to be life minus the d train times in cycle. And we can see how it goes, how it looks now. So we have the cycle keep increasing here, 1 2 3 and so on, until it reaches to the final one. And here you can see remaining life, it's decreasing. So this is the most important value, remaining useful life. Now what we don't want the life column. So what we need to do is to drop it. Life axis 1, which is the columns, and then place equals true. Now what we will do is to make or draw our graph, but this time based on the remaining useful life. So we want to see every parameter, how it changed to in regards to the remaining useful life. So we do this with Seaborn. So we write this syntax. This is a very syntax thing, so I'm just taking it. the figure size is equals 8 and 40, so it's quite long but not very wide, and this is just to show the figures parameters, to show them neatly. So this, now the front size is 8, and just take this. Nine width, we want to make it very short, very small, because we will draw many lines. Every line will represent one engine cycle, also like one engine life. And what do we need to plot? Well, plot items equals list data frame train dot -1. So this one is, we just take the data frame, the data frames, and we just take only from 1 to, well, just this is the basically the time in, or we take it from cycle to RUL. So we don't consider the cycle and the remaining useful lives. We just don't consider them in our plots. Here subplots, and length equals plot items all of them will share the graph. And the thing is, one thing we want to show, that we need to invert the first graph, because remaining life, we want it to start from a high number and then goes to 0, and we don't want traditional graph that we start from 0, and so we just want to invert one of the axis, invert x axis, and now we will start to plot. So these are all, before is just the syntax to make the plot beautiful. Now we need the engine dot unique value for engine here engines, let's plot, let's use part of it, not all of it. From 0 to 20 engine, we change it later, or let's take the middle engines, so from 20 to 30, maybe a little bit more, we take 40, so 20 engine. Of course you can plot more engines as you want. For item we enumerate to plot the plot items, and now we add another syntax for seaborn. Line plot. The data will equal df train and need this one because lot for when engine tt engine equals this engine. And x equals RUL. So data frame engine. The X we will use is RUL, remaining useful life. And Y will be item, this one. And color, just make it black. Black. I think it's already. And the axis will equals this. So this will be AX equals AX0, AX1, AX2, because here we define these plots, this AX, which is the number of plots. I think is okay. Let's run. We didn't have a comma here. Font, figure size, font, font. Font size equals 8. Line width equals 0.1. Yeah, it's good. So now you can see how these graphs, so this is the remaining useful life, and at the beginning many engines, actually most of them, they don't have even have more than 200 remaining useful life, and as they go the engines will reduce. You can see here the LPT coolant bleed, the numbers get deteriorated. HPT coolant bleed also deteriorated. Bleed enthalpy increases as the remaining life approaches to 0. Remember this is inverted plot, so here is a high number and here is a low number, and we can just look into the other things. We have some kind of patterns. Sometimes we don't have real, or feeling that they have a pattern. So this is the graphs. Now we can understand that we need to cut a little bit from the data, about 125 here, because before that is just a straight line. So it's not good to add this data. It will make our data goes to more normal kind of operation engines. So what we need to do we need to cut this, and to do so what we do is df train the remaining useful life, df train also remaining useful life should be more away. This is open. This is more than 125. Okay, we can call it 25. So if it's above 125, we just call it 25, the remaining useful life, because these parameters seems to be constant. So we can do like this. Now we can see how the data looks. And also these plots, how they look. Or we can just take them from here and we put them here. So now with all the datas that have this straight line, it will act as 125. So correlation equals, so this is what we write, and df train dot correlate. So this is the correlation, and now we make a graph. Ax equals plot. This is matplotlib, of course. Plot big size equals 16, 16. Data plot equals SNS dot heat map and correlation. This is camp. It's just the colors. YLGN GNBU. And we run this. And see, we have a problem. Heat map. Oh, sorry. So this is actually, it's actually C map or color map. And now it's working, I hope. So now we can see the correlation between every value and the other values. And the most important value we care about is the remaining useful life. So the correlation graph is very simple. It's just you have this number from 1 to 0, or from 1 to -1, which is represent the correlation between these values, and or between one factor and the other. And one means is directly correlated. So of course RUL is directly correlated to itself, so RUL and RUL. Then also every name here, LPT coolant bleed, and this one LPT coolant bleed will be directly correlated with itself, so it's always one. You will see one here. And this graph is actually in the bottom side and the upper side is the same, so we can use either. And some people even remove the upper side. So what we care about is RUL and how it correlates with other value. You can see high values of this is 0.73 is high, 0.76 is high. Minus and plus is important, but not so important, as we of course we care about how things are related to each other. So if one value increases, the other value decreases, or the opposite side. However, with machine learning, what we do is at the end we will assign weights, and it will be minus or plus this weight. So it matters, but it will be fixed with machine learning algorithms anyway. So correlation works by having two parameters, or connecting them, connecting two parameters and two parameters only. And the way it does by applying Pearson equation, and the equation is basically is this is its equation, and how it works is we have the covariance of xy divided by the divided by the root square of the variance of x and the root square of the variance of y. Now the variance is can be denoted by this equation. So we can see the equation of the variance, and how we calculate it is yi equals or minus y mean square, the summation, over n minus 1. Of course, this one looks familiar because actually the standard deviation is the square root of the variance. So this is actually is the standard variation of the y, and here is also we apply this one, and it will be denoted to the standard deviation of x, and the covariance of xy is we apply this equation, which is xi minus x mean multiplied by yi minus y mean over n minus 1. And this way we can calculate the correlation matrix, or this is how the correlation is calculated. And of course, if we have and we just feed the values here, even if it's that is going to be between 1 and minus 1.